Hi everybody. So let's continue along this thread of filling and drawing primitives. And there's something else I want to talk about. I'm finished now with how to fill triangles and how to fill polygons. We're finished. So I'm going to talk a little bit about what do we do as we're filling them. So this is a really cool topic, shading. And for those who are interested in graphics, often shading is one of those people really get excited about this, and you can do a lot. In fact, I took a whole graduate course just on different kinds of shading, like a whole course after several other graphics courses. So there's a lot going on here. So as we fill a shape, and I'm going to say now triangle because I hope I've convinced you. Let's just stick to triangles. While we're doing that, while turning on and turning, hold on, my mic on? Yeah, okay. While turning on and off the pixels, we can make another decision too. We don't just need to turn the pixels on or off, right? We can set its color. Awesome. So, okay, so what do we do with it? Let me show you what this looks like. I have a triangle. We've learned how to draw the outline with Bressenham's line algorithm. We've now learned to fill it with scanline algorithm. But as I'm filling it, as I'm putting these dots in order, I have to make a decision about what color to make them. Now, these dots, each dot is called a fragment. So just a bit of vocab for you. You'll come across that term, fragment. So each dot is called a fragment. So what do we do with these? There's a lot of really cool stuff we can do. We can put pictures there, we can do reflections, you can do a mirror, all kinds of really cool stuff. But first I'm going to talk about a mathy thing, a coordinate system that we can do with these triangles called barycentric. Now I don't know who Barry is and why he's made himself the center of these things. It should be Jim-centric. I want to be the center. I don't even know if Barry's a person's name, to be honest, but barycentric coordinates. This barycentric coordinates is actually a really big idea in math and physics, and you'll come across it if you've done physics with simulations and masses and things like that. But we're going to only use a very simple narrow form of it for computer graphics. So we've actually already seen this before. But we've only seen it for a line and not a triangle. So I'm going to work through that and show you how we've seen this with a line, extend it to the triangle, and hopefully it'll make a bit more sense. So let's learn about this coordinate system for a triangle. So let's remember first. Remember that this is an annoying piece of software. Okay, remember. Let's remember the parametric form of a line. If you're still not sure about that, it might be a good idea. That's a lime. I'll put the lime in the coconut. There we go. It might be a good idea to go back and review. Okay, so pause the video, go back and watch that if you're still not sure about those parametric line equations. But otherwise, keep going. So if I have a parametric form of a line, then any point on that line, or on the line, can be presented by a weighted combination of the end points. So let's draw that out. I'm going to draw myself a nice little coordinate system. Yay! There was much rejoicing. I'm going to draw 2 dots here. Now if I have this line, and what we've learned is, I'm going to call this vector 1 and vector 2. what we've learned is that any point on this line I can draw by having a proportion of the first one or the portion of the last one. In fact, we saw this in a parametric form before, where the line can be written as 1 minus t, for t from 0 to 1, remember, to v1 plus t of v2. So when t is 0, I get 100% of v1. When t is 1, I get 100% of v2. And otherwise, I get points along the line. So this is kind of like barycentric coordinates. So we'll see how this works. I'm going to write this a little more generically. I'm going to say that p is a combination of u times v plus v times v2. So I'm going to put the u over here and v down there for this point. The combination of those, actually I'm going to erase that for now. We'll come back to that. And the only thing I'll add here is the only difference between the 1 minus t form and the uv form is that in the u plus v form here, I have to spell out the fact that u plus v must equals to 1. It's a constraint on that formula. And we got that for free with our blue one over here. We got that for free with our previous form of this, right? So if this is u and this is v, I can add them together. So 1 minus t plus t, of course, they cancel out, is 1. So to wrap this up, I can take any point in this line and I can write it in the form of u times v1 plus v times v2. As long as u and v add to 1, I'm going to get a point on that line. We've seen this before. It's the same thing as this form right here. It just lets us go across the line and write our point as a balance between v1 and v2. Okay. So I'm going to take my diagram here and I'm going to extend it. I'm going to put another point up here, and I'm going to make a triangle out of it. And this is v3, sure. So far, what I've done is I've made another way to look at this is I've done u times v1 and v times v2. These vectors will linearly interpolate across them, and you get that straight line. Now, I can do the same thing between v1 and v3. Okay, and I just drew that so it's easier to see. So this line here, okay, I can do the exact same thing. I can write it as a parametric equation. So if I'm going to write this out first, I'm going to call this edge 1. So the point on edge 1 is going to be uv1 plus vv2, where u plus v equals 1. Good. Now I'm going to call this edge 2 rather. So I can do the exact same thing on edge 2. On edge 2, it's going to be a linear combination of uv1 plus, this time I need v3. I'm going to use a new variable name here. Instead of using v again and getting confused, I'm going to call that wv3. And again, those two parameters have to add to 1. So u plus w is 1. So what I've done here is the exact same thing. I have a parametric form of this line, and as I go from 100% of v1 to 100% of v3, I'm going to, that's wrong color. I'm going to get these points along this line. It's just an exact same thing, a parametric equation. And for completeness, I'm going to do E3 down here. The point along E3 is going to be WV3 plus, let's use the same numbers, so V times V2, where W plus V is 1. Same thing. So all I've done here is I have 3 parametric equations for these lines, and just using different variables for them, and you'll see why in a minute. But if I take a combination of V3 and V2, as I go from 100% of V3 and 0% of V2, and I reduce that, and I go along my parametric line, I'll get all the points along that line in a parametric fashion. So I just wanted to do this to show you that it's all kind of the same thing. Okay? Let's see if I have some annotations to help this out. Yeah. So on this line, we have u plus v is 1. right? Now, inside my triangle here, I'm going to say W is 0. 0% of V3, okay? So we're going to leave that there. What else do I have for annotations? I think we're good. So I'm going to sum all of this up and tell you, yes, I know, okay, sorry, lost my train of thought there, but I got it back. So on this line, here, Wizzo? I couldn't even read my own writing. What hope do you have? W is 0. Okay. So on this line, U plus V is 1 and W is 0. But what if, and red's a terrible color, if we increase W, as long as we keep our constraint, except I'm going to expand it such that U plus V plus W is 1, what happens? So along this line, I have U plus V of 1, but W is 0. If I increase W, I'm adding more of that vector there, and I'll have to decrease U and V to make up for it because they have to add to 1. So what's going to happen is I'm going to get points inside the triangle. Wow, that's kind of neat. So if I increase W such that U, V, and W equals 1, I'll get points in that triangle. And it turns out that I can get any point in that triangle this way with this general barycentric equation. V1 plus VV2 plus WV3. And this is my general barycentric equation for points in the triangle. And all this tells me is that I can find any point P in this triangle here by taking a portion of V1 right there, a portion of V2 right there, and a portion of V3. And some combination of those. As long as I keep my constraint that U plus V plus W is 1, then I'll get a point in that triangle. So it's just like the parametric line, you can imagine that, except now we've moved into 2 dimensions. So this is barycentric coordinates. Any point in my triangle can be represented this way. Any point in a triangle can be specified in these coordinates. Okay? Basically, as a weighted weighted combination. Weighted just means those U, V's, and W's are weights, right? A weighted combination of the 3 vectors. I should say 3 vertices. We turn them into vectors. Right? I take a little bit of VW1, and if we just stop and think about this, this makes a lot of sense, right? Because if I get if U is at 1, then I'm at V1, so W and V are 0. If V is 1, I'm over at V2. If W is 1, I'm up at V3 and the other ones. As I decrease W and increase the other 2, I can move towards them, okay? So these are barycentric coordinates. A weighted combination of the 3 vertices, yes. And this actually defines a unique coordinate system. And what this means is that a U, V, and W value gives you one single point. And any given point only has U, V, and W. So you can sweep across the triangle by modifying those values and hitting all the points. Defines a unique coordinate system inside the triangle. Cool. So if I have U, V, and W, I can calculate a point inside the triangle. And I know that any point in the triangle can be represented in terms of a portion of V1, a portion of V2, and a portion of V3. You add them up, you can get that point. As long as those portions sum to 1, you won't go outside the triangle. That's really neat. I like this stuff with math because, like, really? I guess that makes sense. But it's really cool that it does work. that if I stick to u, v, and w summing to 1 or less, I'm staying inside the triangle. It's really nice. Okay, so given, oh, come on. So given u, v, and w, then calculating p is easy peasy, right? Right there, the formula. Just multiply them out, you're good to go. However, how do we work in the opposite direction? Given p, what's the u, v, and w? So I'm going to draw a new triangle here. I'm going to draw a little bigger. Biggest triangle is best triangle. All right. So v1, v2, v3. I'm going to call this whole triangle T. So now I have a point in here. I have a point inside my triangle. I'm going to call it P. I got a P. Yay. Wait. I just realized that sounded like I got a P, but I don't because my coffee's still here getting cold. So given P, what is U, V, and W? It's not so easy as you might think. So if I have U, V, and W, I can calculate the P. Here, I can understand that any point can be represented this way in terms of weighting of these vectors. But if I have a P, what U, V, and W values do I have? So that's the next thing I'll talk about. Yeah, good. So I want to make a few observations with this triangle that'll help us out. Okay, 1. P forms, the point P, 3 new triangles inside T. Okay? Right? No big deal. Let's draw them. Cool. P forms 2 new triangles. The other obvious observation is that, okay, I need to label these before I say the next thing. I'm going to call this, because I can't even read my own writing. You poor kids. Sorry? You're not kids. I almost said you poor guys, but that's sexist, so I didn't say poor kids, now that's ageist. I better stop before I say something else. What I was trying to say was I'm going to label these little mini triangles with U, V, and W. That's a wonder why he chose the same letters. So I'm going to call these triangles U, V, and W. And what I want to highlight is that the area of the 3 subtriangles sum to the area of T. Obvious, right? I put a point in, I split it into 3. If I add those areas up, I get the area of the whole triangle. Okay, this is obvious. So why are you telling me? Because the next point isn't so obvious, but it's really cool. The area of the subtriangles is proportional. Area is singular, but triangles is multiple. Are proportional? I'll just fix it. Areas are proportional to the I don't think barycentric is capitalized. I don't think it is someone's name. I should look that up. Barycentric Coordinates. In fact, it turns out that the area, for example, of U divided by the area of the whole triangle, this gives me my U value. So this area here not that area. This area here, if I divide that by the whole triangle, I get what percentage of u with the triangles covered by u, and that's actually my u coordinate. I can use that u over here, u times v1, to get that component of p. And then I'm going to highlight that the area of v divided by the area of t, this is going to be, you guessed it, my v value. So if I shade this one, okay, I shade this, this is going to get me my v value for v2, right? So v times v2, that's my part of my p, and you guessed it, for the last one, I can shade that with my ultra rare red highlighter. This is going to give me my y coordinate for v3. I said y, I meant to say w. So the area of w divided by the area of t is going to give me my w coordinate. So that's really neat. So if I get the area of a triangle, I divide it by the area of the whole triangle, I'm splitting this up. And this starts to make sense. The pieces start to make sense when you realize if I add these three together, right, u plus v plus w must equal to 1. This is 1, because u plus v plus w, add these three areas together, and of course, they add to 1 because you're dividing by the triangle. If you think percentages, it's obvious. If I add this 3 together, I get 100%. So I think this is really cool. If we know the areas of these little triangles, we have a p, and my p has disappeared. Let's see if I can put a p in there because of all my shading. Yeah. We can then calculate the barycentric coordinates by the portion of the that area. So how on earth do we get area of a triangle? Cross product. It's almost as if we learned that for a reason. Cross product. And what's really cool, I want you to take this now, if you go back, look at the point in triangle test, you're going to see this is actually pretty much what we're doing already. We have a P in the middle of the triangle. We draw a vector to it. We cross product it with the edge. We draw another vector. We cross product it with the edge. We draw another vector. Hey, our point and triangle test gives us the areas of these three. We have it. So this is one more reason why I said that we use the scanline point and triangle test, because it's really useful to have that information. The point in triangle test gives us the values we need. So I wouldn't say it's free, but we're definitely doubling down. If we do the point and triangle, we already have our barycentric coordinates. The last thing I'll mention, and because it's common to see this in examples, you'll see, and as soon as you see them, it'll look familiar. Oh, maybe I'll pause the video after and find an example. That's a good idea. But it's common to shade barycentric coordinates. Okay, so you can see how your triangle and the orientations and things like that. And all that you do there is you set R, G, and B values of your color. I should make it capital to be U, V, and W, or some mix. It doesn't really matter which one's which at this point, unless you need to know which one is U, and then you keep your orientation. So you can shade them. So that's it. That's barycentric coordinates. Now, if you're struggling with the parametric line stuff, then this is going to hurt you even more. So it is a good time to go back and review that and then come watch this video again. But the intuition points here is that any point in the triangle can be defined by this weighted combination of the the weighted combination of the actual vertices of the triangle, as long as those weights sum to 1, will be inside that triangle, right? You can actually look at this as another way of understanding the point and triangle test. Let's solve for u, v, and w. If they're bigger than 1, it's outside the triangle, right? Perfect. It's another way to do it. All right, so I'll leave that here. Oh, I'm going to pause and come back with a picture. So here we are. You can see this is an example of what it looks like. As 100% red, it's this corner, 100% green is this corner, and 100% blue is that corner. And it never gets to bright white in the middle, because to get bright white, you need 1, 1, 1, which sums to 3. It can only sum to 1. So at the very middle, you're going to get like a perfect dull gray, 0.3, 0.3, 0.3, right in the really middle. And the exact how this breaks down will depend on the orientation of the triangle, the order of your vertices, and also the ratio and the order of your triangle. The ratio and the, I'm trying to say the shape of the triangle. Okay, thanks. Done this video.